So we're looking at intersections of three planes continued. So we saw that we could have three planes intersect in a single point. And that seems, if you just randomly came up with three planes, chances are they're going to intersect in a single point. We've seen the situation where planes are parallel and they don't intersect at all. That's really pretty easy to pick up because the normals end up just being scalar multiples of each other. Coincident planes, that's also pretty easy. Once again, the normals are scalar multiples, but actually the whole plane equation is a scalar multiple. So it's pretty easy to pick up the coincident and the parallel situation. It's also pretty easy when they intersect in a point. You don't have that. Here's the last situation that we're looking at today. This has all three planes intersecting in a single line. So this line where they all intersect, we say is a solution to the system. And this last situation, they're intersecting in this pup tent formation. I can find a line where two of the planes intersect, and that would be the solution to two equations and two unknowns. It would be a line, but there is no place where all three equations intersect. So this technically has no solution. So we're going to look at two examples where this happens. We looked at matrices, and matrices are sort of fall under the heading of not really being all that big a deal, a little bit easier to write with, and later on they become important. But right now, really all we're doing, we're just transferring the coefficients into this matrix form, and we're just discarding the variables and forgetting about them. Okay, so there we go. We've already put this into matrix form. The goal of Gaussian elimination, when we're doing Gaussian elimination, we want to have a 1 up here in the top left corner, and we want to have zeros in this little triangle here so that I can read off my value for Z directly from this matrix, and I can substitute it back up. I also like to have a 1 here so that I can eliminate the X in these rows a little bit easier, and I want to have a 1 here so I can eliminate the Y a little bit easier. Okay, I've turned this system into a matrix. Really, I want a 1 up here, and I'd like to have a 0 there because it's handy, and so we are handily starting off with a line that's got a 1 in the first position. So I'm going to put row 3 up here. 1, 1, 1 is 1. I have a 0 here, so I'm going to put row 2 here. And I'm going to try and not make any mistakes. I'm going to teach this row a lesson in just a second. I'm going to put it down at the bottom, and I'm going to start doing my elimination there. Okay, hopefully I haven't made any transcription errors. This is where we want to go. So let's do some elimination. Okay, the top line, once again, I am eminently happy with it. So 1, 1, 1, 1. There we go. Second line, also, actually, I'm eminently happy with it. So there we go. There's the second line. The third line, there's a 2 here. I want to eliminate it. And so I'm going to use, I'm going to subtract 2 times row 1. So I'm going to take row 3 from my previous matrix here, and I'm going to subtract 2 times row 1. And this is where hopefully I get my math right. 2 minus 2 times 1 is 0. Okay, I've got what I wanted there. Negative 1 minus 2 times 1 is negative 3. And negative 1 minus 2 times 1 is negative 3. And last one, 2 minus 2 times 1 is 0. Ho, 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 look what's happening. My next step is to try and get a 0 here, and I'll go through that whole scenario. But can you tell me what's happened here? No? Okay. You'll see. Okay. Once again, line 1, happy with it. Line 2, so far, so good. I'm happy with it. Line 3, I have a 0 there. I want to make a 0 here so that I can determine with great exactitude what my Z value is. So what I'm going to do is I'm going to take row 3 and I'm going to add 3 times row 2 to it. Okay, so -3 plus 3 times 1 is 0. -3 plus 3 times 1 is 0. And 0 plus 3 times 0, even I can do that one. 0 plus 3 times 0 is just 0. All right. Okay. We have to pause for a minute. So if you were a cat, pause for a minute. This means that 0x plus 0y plus 0z is equal to 0. Okay. Can you tell me, yeah, who knew? Can you tell me values of x, y, and z that satisfy this relationship? Trick question, right? Yeah, the fact is any value of x, y, and z works, right? 0 times 0 times 0 of anything is going to be 0. And so that actually means that I found out these two planes intersect in a line, and this plane intersects in a line with those two planes. And so we have scenario 1 up here, which is the 10 army piece in Risk, if you've ever played that game. All right. Okay. So this is the line. Let's come up with the equation of the line, and that's going to be the solution to our system. This one's nice and easy. So this means that y plus z is equal to 0. Okay, so that is a relationship that satisfies this. So what I'm going to do, I'm going to let z equal t, and that's going to be equal to, that means that y plus t is equal to 0. So that means that y is equal to -t. And if I go back to my first line here, this means that x plus y plus z is equal to 1. That means that x plus and y is -t. So I'm going to say x minus t plus z, which is t, is equal to 1. There we go. Let's revel in the disorder here. Okay, and that means that x is equal to 1. Okay, so there is my parametric solution of this line. So x is 1, y is -t, and z is equal to t. So there's the parametric form of that line right there. Okay, so that's 3 planes intersecting in a line. The internet looks bored right now. No? Internet's okay? All right, hooray. Let's look at the pup tent example. It's going to be a little bit different. We're going to get to the scenario where there's no solution. Nothing works. It's inconsistent. But it does look like a much more fun intersection than that one. So if it gets points, it's inconsistent, but at least it's fun. Okay. Here we go. For x plus y minus z is equal to 5. 1x plus 3y plus z is equal to -2. And 9x plus 5y minus z is equal to 1. Okay. Let's turn this into a matrix. Put a line down there. It's called the Augmented Matrix, by the way. The line means that's where the equal signs would go. And I can set this up. Which equation should I put into the first position to reach my goal? This one, or this one?
The second one.
The second one. Yeah, there's a 1 here already. So I'm going to put that in the first position, and it's just going to make my life easier. Okay, 1, 3, 1.
So what do you do then when there is no 1 in the equation? It's like if there was no, just like plain old 1.
Yeah, if there's no
Did you
1,
pick like the lowest?
pardon me?
Did you pick like the lowest one?
You can put the lowest one in, or you can just set all the coefficients in and then, you know, try and subtract them so that you get a 1 there.
Okay.
Yeah, really, it's just elimination using the equations will kind of work anyway. But yeah,
Okay.
it's you're just doing elimination for equations and 3 unknowns. Nice to get a 1 there. You might have to divide through. So if you wound up with a 3 here, you could divide through by 3, and it would wind up sometimes being really ugly fractions. Yeah. So fortunately, our examples don't have fractions in them. I make enough mistakes without having fractions in it. So, all right. Okay. So I'm going to put equation 2 in this position for 1, -1, 5. And I'm going to put equation 3 down here. 9, 5, -1, 1. Okay. Good. Happy with the first line. No fractions, too. To get row 2, I want a 0 here, so I'm going to subtract 4 times row 1. So this is going to be row 2 minus 4 times row 1. So 4 minus 4 times 1 is 0. That's what I wanted to do. 1 minus 4 times 3 is -11. -1 minus 4 times 1 is -5. Good. And 5 minus 4 times -2, which is the same thing as 5 plus 8. Is this, did I get this right? Is this -13?
Shouldn't it be just positive 13? Because you're adding a negative.
Oh, you and your getting your negatives right. I like that. Okay. So I have a 9 here. I don't like that. And so I'm going to do row 3 minus 9 times row 1. Okay. And magically, you notice that since I have a 1 here, it makes it super easy to get rid of these x's. 9 minus 9 is 0. 5 minus 3 times 9, is that right? Is -22?
Yep.
Okay. And then -1 minus 9 times 1 is -10. Very good. And finally, 1 minus 9 times -2 is going to be like adding 18. This is 19. Did I get that part right?
That's what I thought.
Hooray. Okay, good. Okay, so let's watch out with what's happening here. You'll notice that now we have the equations of 2 lines, and the normals are basically scalar multiples of each other. So this thing is going to go south. Either it's going to be consistent or it's going to be inconsistent. My bet is on inconsistent.
Does it matter that what they're equal to isn't a scalar multiple? Like the equation itself is, but the rest of it isn't?
It sure does, yeah. Okay, so basically, if these were the same, exactly the same line, what would I have in this position?
Oh, you'd have, yeah, okay.
Yeah, if this was a 26, these would be the same thing, okay? That would mean I've got scenario 1. But I didn't. What did I have here? Was it, oh, now I've got to redo the math. That's horrifying. Okay. So anyways, so.
It was just 19, wasn't it? It was just 19.
Yeah, it was 19. Oh, thank you for saving me. Okay, I didn't want to do that. That would be extra work. Okay, so 0, -11, -5, 13, and 0. There's a -22 here. I want to make it into a 0 to reach my goal in life. So I'm going to take row 3. I'm going to subtract 2 times row 2. And so this is going to become a 0. But horrifyingly, this becomes a 0 as well. And then 19 minus 26 is -7. Okay, so this is where we pause and we go, oh my goodness, 0x plus 0y plus 0z is equal to -7. What value of x, y, and z makes this true? There isn't one. That's right. There's no such thing. This has no solution then. Okay. Really, what I found out here was that two of the planes are intersecting in a line, but the third plane doesn't intersect that line anywhere. Okay, so this is no solution. We call it inconsistent. Even if it's more fun, it is how do you spell consistent? There we go. It is an inconsistent system. They do not intersect in the same place. And we're done. A question could say, what is the line of intersection of two planes? And you'd have to turn this into parametric form, okay? But no solution to the system of three equations and three unknowns. And super quickly, I'm going to talk about what somebody in the video conference mentioned a little bit early, which is that in both of these situations, this line of intersection is perpendicular to the three normals, interestingly enough. And all of these lines of intersection are perpendicular to three normals of these planes. So if I have this scenario where they're intersecting in either of these cases, the dot cross product, which is the volume of a parallelepiped made by the three vectors, will be equal to 0. The audience has been replaced by a kettle drum. Okay, yeah, so if I take this, so and it doesn't matter which normal I choose, if normal 1 dot the cross product of normal 2 and normal 3, and I can do them in any order, equals 0, then I have one of these two scenarios here, okay? So I will leave it as an exercise. If you do the dot cross product, which is the cross product of any of the two of the normals with the dot product, it's going to be equal to 0. And so that's it. That's the last lesson. It's all over. I'm going to stop the broadcast.